In this chapter we deal with work, kinetic energy, potential energy, and conservation of energy. What are the concepts involved? Average power, kinetic energy, net work, power, work done by a force, work energy theorem, conservative force, conserved quantity, energy conservation, equilibrium point, exact differential, mechanical energy, non-conservative force, non-renewable, potential energy diagram, potential energy difference, renewable, turning point. In this video we have included potential Z main/advanced/NEET questions. Problem 1. A 75.0 kg painter climbs a ladder that is 2.75 m long leaning against a vertical wall. The ladder makes a 30-degree angle with the wall. A. How much work does gravity do on the painter? B. Does the answer to part A depend on whether the painter climbs at constant speed or accelerates up the ladder? Identify Newton's second law, friction force, weight-free body diagram. Setup. Please see P1 setup.png. Note that weight equals mass multiplied by acceleration due to gravity equal to 50 n. Execute. Please see the PNG P1 solution clearly. Option B is correct. Problem 2. Z Main 2026, online, January 21st evening shift. Please see the PNG P2. Identify change in kinetic energy equals work done. Setup. Please see the PNG P2 solution. Execute. Please see the PNG P2 solution. As the PNG shows, B is the right answer. Please like, share and subscribe to Physics channel. To get free 1. Specific doubt clearance, problem solution guidance. 2. Download concept cards, formula cards. 3. Listen to downloaded chapters anywhere. This is an XIITN IIT Madras channel. Problem 3. Please see the PNG P3.png. Consider a particle on which several forces act, 1. Of which F is known to be constant in time. F has I component of 3 newtons and J component of 4 newtons. As a result, the particle moves along the x-axis from x equals 0 to x equals 5 m in some time interval. What is the work done by the force F? Solution. Since F is constant and distance moved has no y component, work done equals x component of F multiplied by 5 equals 3x. 5 equals 15 newtons. Problem 4. Consider a particle on which several forces act, 1. Of which is known to be constant in time. F has I component of 3 newtons and J component of 4 newtons. As a result, the particle moves along a straight path from a Cartesian coordinate of 0 m, 0 m, to 5 m, 6 m. What is the work done by the force F? Please see also P4. Solution. We use equation 1 from the card, which may be read as modulus of F multiplied by modulus of R multiplied by cos of angle between the two vectors. R makes an angle of 50 degrees. F makes angle of 37 degrees. Angle between the two is 13 degrees. Magnitude of F is 25 n. Magnitude of R is square root of 25 plus 36 equal to 7.8. Result equals 25x. 7.8x cos 13 equals 38. Problem 5. A box 10.0 kilograms computer monitor is dragged by friction 5.50 m up along the moving surface of a conveyor belt inclined at an angle of 36.9 degrees above the horizontal. If the monitor's speed is a constant 2.10 centimeters s, how much work is done on the monitor by A. Friction, B. Gravity, and C. The normal force of the conveyor belt? Identify work done by a force. Equation 1 in the card, equilibrium conditions. Setup. Please see the PNG P5 setup. Execute. Note that friction force is directed upward and there is no motion relative to belt, as the belt is moving at constant speed. Friction force equals mg sine 36.9. Work done equals friction force multiplied by 5.5 meters equals 324 J. B. Work done by gravity is negative as the box moves up. Value equals 5.5 m multiplied by sine 36.9 multiplied by box mass multiplied by g. Dash 324 J. C. There is no displacement in the direction of n, so 0. Problem 6. 6.23. A sled with mass 12.00 kilograms moves in a straight line on a frictionless horizontal surface. At one point in its path, its speed is 4 meters per second. After it has traveled 2.50 m beyond this point, its speed is 6 meters per second. Find the force acting on the sled, assuming that this force is constant and that it acts in the direction of the sled's motion. Use the work, energy theorem to 6.25 identify, apply equation 7 in the card. Set up, change in kinetic energy equals work done by the force. Execute. Please see P6 solution for detail. Evaluate, ANS 48 and the force is in the direction of the displacement, so the force does positive work and the kinetic energy of the object increases. Problem 7. A 6.0 kilograms box moving at 3.0 m/s on a horizontal, frictionless surface runs into one end of a light horizontal spring of force constant 75 N/cm that is fixed at the other end. Use the work, energy theorem to find the maximum compression of the spring. Identify, apply the work energy theorem. Set up, let point 1 be just before the box reaches the end of the spring and let point 2 be where the spring has maximum compression and the box has momentarily come to rest. Execute, CPNGP7 solution. Evaluate, the compression of the spring increases when either 0 V or M increases and decreases when K increases, stiffer spring. Problem 8. A force is applied to a 2.0 kilograms radio-controlled model car, parallel to the x-axis as it moves along a straight track. The x component of the force varies with the x-coordinate of the car as shown in figure. Problem 8. Calculate the work done by the force when the car moves from a, x equals 0 to x equals 3, b, x equals 3 to x equals 4, c, x equals 4 to x equals 7, d, x equals 0 to x equals 7, e, x equals 7.0 m to x equals 2.0 m. Identify and set up, the magnitude of the work done by F equals the area under the F versus X curve. The work is positive when F and the displacement are in the same direction, it is negative when they are in opposite directions. Execute, A, F is positive and the displacement X is positive, so W equals 4.0 J. B, during this displacement F equals 0, W equals 0. C, F is negative, X is positive, area in the last part is half multiplied by 2 multiplied by 1 equals dash 1.0 J. D, the work is the sum of the answers to parts A, B, and C, so W equals 3.0 J. E, the work done for x equals 7 to x equals 3 is 1.0 J. This work is positive since the displacement and the force are both in the direction x. The magnitude of the work done for x equals 3 to x equals 2 is 2.0 J, the area under F versus x. This work is negative since the displacement is in the direction x and the force is in the plus x direction, thus W equals 1 J, 2 J equals dash 1 J. Problem 9. A ski tow operates on a 15.0 degrees slope of length 300 m. The rope moves at 12.0 km per hour and provides power for 50 riders at one time, with an average mass per rider of 70.0 kilograms. Estimate the power required to operate the tow. Please P9 solution. Problem 10. A crate of mass m starts from rest at the top of a frictionless ramp, inclined at an angle alpha above the horizontal. Find its speed at the bottom of the ramp, a distance d from where it started. Do this in two ways. Take the level at which the potential energy is 0 to be a, at the bottom of the ramp with y positive upward, and b, at the top of the ramp with y positive upward. C. Why didn't the normal force enter into your solution? Identify motion in single direction. Setup. Please see P10 solution. Execute. Please see the PNG P10 solution. Evaluate. When we use gravum g equals, we can take any point as 0 y equals, but we must take y plus to be upward. Problem 11. A force of 800 N stretches a certain spring a distance of 0.200 m. A. What is the potential energy of the spring when it is stretched 0.200 m? B. What is its potential energy when it is compressed 5.00 centimeters? Please see P11 solution PNG. Problem 12. You are asked to design a spring that will give a 1160 kilograms satellite a speed of relative to an orbiting space shuttle. Your spring is to give the satellite a maximum acceleration of 5.00 g. The spring's mass, the recoil kinetic energy of the shuttle, and changes in gravitational potential energy will all be negligible. A. What must the force constant of the spring be? B. What distance must the spring be compressed? Please see P12 solution PNG. Problem 13. The Great Sandini is a 60 kg circus performer who is shot from a cannon, actually a spring gun. You don't find many men of his caliber, so you help him design a new gun. This new gun has a very large spring with a very small mass and a force constant of 1100 N/m that he will compress with a force of 4400 N. The inside of the gun barrel is coated with Teflon, so the average friction force will be only 40 N during the 4.0 m he moves in the barrel. At what speed will he emerge from the end of the barrel? 2.5 m above his initial rest position? Please see P13 Solnfig and P13 solution. Problem 14. A 12.0 N force with a fixed orientation does work on a particle as the particle moves through the three-dimensional displacement vector d equals 2.0 I, 4.0 j plus 3.0 k. M. What is the angle between the force and the displacement if the change in the particles kinetic energy is a. 30.0 j and b. minus 30.0 j? Please see P14 solution. Problem 15. A cord is used to vertically lower an initially stationary block of mass m at a constant downward acceleration of g/4. When the block has fallen a distance d, find a. the work done by the cord's force on the block, b. the work done by the gravitational force on the block, c. the kinetic energy of the block, and d. the speed of the block. A. Using Newton's second law, T equals 3 mg/4 P15 solution. As t and distance moved are in opposite directions, work done equals Td equals -3 mg/4. B. Work done by the gravitational force equals mgh equals mgd. C. Kinetic energy equals T.d mgd equals -3 mg/4 plus mgd equals mgd/4. D. Using C, V equals square root of gd/2. Thank you for your patience.